virtual star parties on the Fort Worth Astronomical Society YouTube channel.
Somebody has to, so.
Right. Okay, so take it away.
Thank you very much. So I have everything set up on my machine, and I'm just going to be broadcasting out on everything that I do. It's a nice little Chiron I've got. So I kind of started collecting meteorites when was it? Not too long ago, but I think it's about 3 years ago now. And I actually found a dealer on not Astromars, it was Cloudy Nights. And he had several meteorites for sale. And I thought, well, I don't have any meteorites. That'd be kind of cool. So I bought one. And then that was really cool. And my wife thought it was pretty neat. So I started getting more and more and more. And I actually had a deal with a bunch of them. So I thought, you know, this would be really cool if I could get more and get a wide variety of them so I can use them as outreach for our club. And that's what I did. So now I have a rather large collection. A lot of them, I don't have huge ones, but I have fairly small ones. And oh yeah, that reminds me, I'm going to pull one more out of the back. And it's kind of it's kind of grown, but it's gotten to the point where I use them for outreach, or let me rephrase that. In the before times, I used them for outreach, and I was able to take them out to star parties and show them out. I took them to my kids' school. We did various events at the Fort Worth Museum of Science and History, where we would display the meteorites, display telescopes, talk about the club, and actually let people handle them. So most people have never touched a meteorite. They've come close, maybe to the museum. I know at NASA, they actually have a lunar meteorite down here in Houston. It is embedded in lucite with a lucite cover on top of it. And if you want to touch it, you have to stick your hand in like this and then maneuver it around, and then you can rub it just a little bit, and that's it. That's as close as you can get. But you're touching a piece of the moon. Well, I actually have lunar meteorites. So I actually pull these out during the star parties and during events, and I can take one, I can put it in a child's hand. I won't tell them what it is, but I'll tell their parents, get your camera ready. And then I say, can you guess where this is from? And they never guess, but I say, this is a moon rock. It's a genuine moon rock from the moon. It is a fragment of a rock that was blasted off of the moon by an asteroid, went around and around and around, and eventually landed in Northwest Africa, in the Sahara. And they always get a big smile on their face, and that's when the parents get a nice picture. So on to the presentation. This is kind of, this is a presentation I did for our club just over a year ago, and I've modified it somewhat. So this is kind of a general overview on meteorites, on asteroids, why they're important, where they come from, what they look like. This doesn't really get into deep classification because while it's interesting for a lot of people, it's also not interesting at all for even more people. So we'll go ahead and continue. I'll switch over. There we go. Oh, well, it's close. So asteroids, meteoroids, meteors, and meteorites. On the left, we have an image of a actual asteroid. And on the right, we have an image of a meteorite sitting on the ground in the Sahara, what it looks like in its quote unquote natural state. Yep. There we go. So asteroids, pretty much anything bigger than 1 meter and smaller than a planet, or now a dwarf planet, is considered an asteroid. So Ceres was the largest asteroid, and now it's called a dwarf planet instead. Meteoroids are anything smaller than 1 meter, down to grains of dust. So that's the general debris in the solar system. And this image over here is Ryugu. This was the this is an image taken by was it Hayabusa 2, the Japanese probe that orbited it. This is just it's kind of this cuboidal shape almost, and it's about 0.85 to 0.88 kilometers in diameter. It's not very big at all. This is pretty much a rubble pile, and we'll get into that. So meteor. A meteor is the visible path of a meteoroid as it enters the Earth's atmosphere. If it's glowing, it's a meteor. And then if it hits the ground, it is now a meteorite. And we call that lithobraking when it hits the ground. If you've ever played Kerbal Space Program, you know what lithobraking is. So it comes from the Greek word meteoros, meaning high in the air. The Greeks knew it was somewhere up there. They just didn't know how high it was exactly. They just knew it was very, very high. Asteroids, large objects anywhere from a meter to 500 kilometers across. And the larger ones are differentiated just like planets. They, when they formed, it was melt material just from gravitational potential energy of stuff just impacting as it grew. So it melted. The more dense iron nickel went down to the core. So they have a differentiated core, a mantle, and a crust. Smaller asteroids, like Ryugu we saw before, those are rubble piles. They're pretty much just held together by gravity, a strong enough hit, and they would just shatter. And many of our meteorites do come from impacts of asteroids. So the C types, the chondrite asteroids, they're the most common. It's clay, it's silicates, they're rather dark, and they are the oldest objects in the solar system that are basically untouched. And what we say is that they haven't experienced much melt. And they're important, and we'll get into why they're important, because they're composed of chondrites, which have little bitty chondrules in it. And chondrules are basically the little time capsules from the early formation of the solar system. We have the stonies that are made of silicate materials and nickel irons. These are usually broken up pieces of larger asteroids or planets, planetesimals. And the M types are the metallic nickel irons. And it depends on where they formed in the solar system. That has to do a lot with the material. We'll get into that as well. For a lot of these, the metallics, these are also the remnants of cores of larger planetesimals, dwarf planets, differentiated asteroids that got blown apart as well. Asteroids, how did we find them? Well, they're really hard to see, but with larger telescopes, we were able to see them. So the first one, Ceres, we found in 1801, then Pallas in 1802, Juno, Vesta, Astrea, and we keep finding them as we find more and more as we look for deeper into space with bigger and bigger telescopes. So by 1868, we were able to find 100 asteroids. By 1921, 1,000, then 10,000 by 81. And then we have this huge jump, 100,000 in the year 2000. And then in only 9 years, we got another we're up to 500,000. Right now, we're just under 1 million known asteroids. And then they get named. I think we have like close to 24,000 right now. When I keep trying to find updated numbers, and they're always several months behind. And there's a reason why for the jump. So this is actually a video. Let's see how well this works. I'm not really sure. So we're looking 1979, 1980. We're looking at sky surveys. People are taking photos. This is back in the film age. So we're taking photos. We're trying to find new asteroids. And this is day by day by day when asteroids were discovered. And you can see every once in a while, there's a big jump. There's a couple, and then there are big jumps. Those are the sky surveys. So people are taking pictures several nights in a row, and they're analyzing that for anything that moves, just wide angle sky surveys. I'm going to jump ahead because this is kind of boring. We're going to go a little bit further, about here we go. Let's look about 1995. We start getting into serious sky surveys. And at this point, we're starting to use digital cameras. They're not the greatest digital cameras, but they still work. They still help us find stuff. So at this point, nightly, we're discovering several hundred in the late 90s. And you can see these streams going out where it's basically at midnight, close to midnight, as deep in the night as they can. They're taking images in one area of the sky, and they're trying to get as many asteroids as they can. They're trying to find them. And right here in the year just before 2000, we see systematic sky surveys being done. So we're finding more, basically 1,000 a night sometimes. Various sizes. We're also finding a lot of near Earth asteroids. So if you look right about there, where Earth is, we're finding a lot of Earth ones. Here we have, I can't remember which one's trailing, which one's leading, but we have Trojans and we have Greeks, or we have Greeks here, we have Trojans. These are the ones that follow and lead Jupiter, the Greek camp and the Trojan camp. We found some, but now these automated sky surveys are finding lots and lots and lots. So here we're pretty close to 500,000 in 2007. And now we're getting into serious sky surveys. And very soon we'll get into satellite surveys as well, where it's not just stuff that's earthbound. We're finding stuff, you'll see these spikes that go, there we go. So these are satellite surveys that are going on, that are constantly going on, where they're able to, from orbit, find more find more asteroids, because we're not limited by nighttime anymore. We're able to kind of block off the sun here and go straight ahead. And this goes on quite a bit. I don't know if y'all have seen these, but the numbers here are ridiculous. It's thousands of new asteroids found every single night, plus all these near Earth asteroids. So those are the ones that really concern us, not the stuff that stays out in the asteroid belt. But that's it, because that's all the data I have. So yeah, we're at a pretty close to 1 million found asteroids at this time, and we think that might be anywhere from 10 to 20% of what's really out there. So there's quite a bit more to find. All right, meteoroids, smaller than asteroids, grains of dust up to about 1 meter. It's the general space debris all around the solar system. It's broken bits of asteroids, of comets, and it's silicates and it's metals, all sorts of stuff. And because they're so small, and typically because they're so dark, they're very, very hard to find and see before they enter the atmosphere. So it's always a surprise for those. And most meteors are pretty much pea-size to softball size, and they burn up completely in the atmosphere. And the reason is, even for larger ones, 95% of the 95% of the meteoroid is burned up as it comes through. Less than 5% typically lands on the ground. So if you have something that's small, softball size, it will pretty much burn up just into dust. Usually the bigger stuff, it's got to be somewhere, I'm going to call it about 3 to 4 feet across, that's going to have something which can land. Anything smaller than that, it typically just goes. So for meteors, for the really small stuff, most of it comes from comets, and we have our meteor showers. Okay, so typically they'll hit the atmosphere anywhere from 11 kilometers a second to 72 kilometers a second. It depends on entirely on the orbit, how it's coming in. Is it impacting the Earth this way? Is it coming in from behind? Is it hitting the side? What angle it is? Whole lot of factors. We don't typically worry about it, but they typically last for a second. What you're seeing right here is the real-time image of a Perseid coming across, and this is about the size of a marble. It's fairly small, but it's very, very bright. And stuff like this burns up typically between 80 kilometers and 60 kilometers up in the atmosphere. So it's very, very high up. And even though it's so small, it's very, very bright. So I don't know if y'all knew that it was quite that high. I didn't realize that at the time when I found out, but it is very, very high. And there's a, when I do these outreach events, people will tell me, well, I saw this meteor, I saw this meteorite, typically I saw a meteor up in the sky. And one guy actually told me that they were out on their grandpa's farm when he was a kid, and it was very, very dark, and they were looking up at the stars, and they saw a meteor, and it streaked across the sky, and it was bright, and then it faded out, and it was directly over their heads, and then they heard it land in the trees a couple hundred yards away. And I just had to break it to him that no, it didn't land in the trees. You probably heard an armadillo or a raccoon or a possum or something else, but that it is so very high, and you're seeing it. If it's not directly overhead, it can be miles and miles away. And we'll get into distance in just a bit, but it can be very, very far away, but it is so bright, even though it's so small. the chances that it's going to land on you are pretty minuscule. So fireballs are the very bright meteors, brighter than the planet Venus. It can last a few seconds. It can last actually a little bit more than just a few seconds. And the color depends on the composition. What elements are there to burn up? And you typically see stuff kind of falling off as well. Now, I once thought I saw a large fireball in the Grand Canyon. I was actually hiking there at the bottom, hiking back up in the summer. I highly don't recommend hiking the Grand Canyon in the summer. It is very, very hot. It was so hot that I was hiking out at night. And as I was going, I saw the color suddenly appear in the landscape around me. And I looked around. My first thought was, well, there's a helicopter going to rescue someone. And I didn't hear a helicopter. And then I thought, well, someone set off a flare. Why would they set off a flare in the Grand Canyon? Because all I could see in the canyon walls were just lit up all around me. And it was kind of flickering. And I thought, well, that's probably not a flare. And I thought, bolide, it's a meteorite or meteor. And I looked up and I saw just the very end of something going over the horizon. And it had been up maybe 10 seconds or so. And I thought I had seen a beautiful, beautiful fireball. Years later, I found out it wasn't. It turned out it was old Russian space debris that had come down. And the reason why I found out is because it was traveling much, much slower than a typical meteor or fireball or a bolide. So in this case, bolides are large fireballs that break up or explode. And these are typically small size asteroid. They can last a couple seconds, couple more, depending on how fast they're going. Sometimes they explode in the atmosphere. Sometimes they skip off the atmosphere and keep on going. And then we have Chelyabinsk. So the Chelyabinsk super bolide back in 2013. So that's what, 8 years ago now, just over 8 years. So this is about 20 meters across, 66 feet. It exploded over or near Chelyabinsk, Russia. So this image right here, this video, is from 160 kilometers away, about 100 miles away. And it is, as it comes in, it's only about 18 seconds. So you can see it enter in, and then it comes in, gets very, very bright, and that's the explosion. And then it kind of peters out. So you think it doesn't look very high up in the sky. It looks like it's very, very low in the atmosphere. Well, it's not. This right here, next chart will show exactly what it looks like. I'll just play it again just so you can see it. You see it enter, and it's burning up, burning up, burning up, burning up. And then it starts to hit some of the thicker atmosphere, and it slows down dramatically and explodes. And the bits that fall off here, they're already moving a whole lot slower. So this right here is that big explosion that we saw. And as it comes in, sorry, I only had it in Spanish, just over about 90 to 100 kilometers, it starts to burn up. And once it hits the mesopause, it burns up even more. But then it really doesn't really explode until it gets into the stratosphere. So 50 kilometers up, actually in this case, I think it was about 30 kilometers up, is where the actual explosion was. So this is high above the troposphere, high above all the weather. This is higher than airplanes fly, typically, is where it exploded. So very, very high. It's still very, very high up. So this, at 100 miles away, it's quite a bit of distance. So it's deceptive. You think it's lower in the sky. You see all these clouds over here, but these clouds are within, 10 miles, a dozen miles, maybe 20 miles of the location. This is much, much further out. When we're looking at little pieces, this is actually a very small piece sitting out on the ice. This is a cut section of a larger piece, and you can see all these fragments, the cracks through here. These are stress fractures from coming through the atmosphere and breaking up. Rapid deceleration and the explosion. It's not really from heat. And we'll show what that is. This black stuff, this is called the fusion crust. The fusion crust is, it's burnt material, but it's very, very thin. And on here, the actual fusion crust is only at the very, very, very edge of it and does not extend to the inside. And we'll show that off later as well. So typically about 150 tons on the average of material falls on the Earth each day. Most of it burns up or falls in the ocean because the oceans comprise most of the surface of the Earth. And we find most meteorites in deserts. The reason is, if it falls in the forest, would anyone ever find it? If it falls in a cornfield, would anyone ever find it? If it falls in your backyard, would you find it? Maybe not. Maybe you wouldn't even notice it. Most people wouldn't. So meteorite falls. These are observed events, fireballs, bolides that are tracked, and then you go find where you think the impact is, and you find fresh meteorites. Meteorite finds, the meteorites that you find from an unknown fall, and there's no telling how old it could be. Some are incredibly weathered. They've been there for centuries, millennia even, and some may have only been there a couple days or a couple of weeks. Kind of luck of the draw. This is a meteorite hunter that I've spoken to on several occasions. This is Tomasz Jakubowski and one of his friends, Marcin Chimała. They're both Polish meteorite hunters, and I've talked to them on several occasions. I've gotten meteorites from them. I'm Polish as well, so it's quite nice. I was actually going to meet Marcin last year. We had planned on visiting family in Poland in August of 2020, and one of my plans was actually to go to see him and to go to a rather well-known meteorite field in Poland called Mrozko, where there are several impact craters, and that didn't happen. So we're pushing that trip off a little bit further. But they're really, really nice guys, and Marcin is very, very good at slicing meteorites. He's actually one of the best slicers in Europe. He's just very, very good. And I actually have one that he did. Actually, I have several that he did. So what do meteorites look like in the wild? Pretty much this. This is Tomasz in the Sahara. So this is, I believe this is in Morocco. And the funny thing is they keep their finds secret. They don't tell anyone exactly where they find them because there are certain areas. It's not that they collect more meteorites. It's just that it's much easier to find meteorites there. And the Sahara is rather large. So the places that they like to go to, that they go through every couple of years and scan through, they like to keep them kind of secret. So they won't tell you exactly where they find them, but pretty close by. But here's what you see. You see this burnt black looking rock sitting out, sometimes buried just a tiny bit into the surface, but it looks completely different than the rocks around it. They just don't fit. And that's what you look for with meteorites. So here they're marking where they found it in situ. They have the GPS, and then you can see they've kind of, they photoshopped out the exact location of where it is for the picture, but they do keep records of it. And this also gives a quick scale, so you know how big this GPS device is, so you can see just how big these two meteorites are. And again, they just don't fit in the environment that they're at. They just look different. So how do we categorize meteorites? We can do it one of two ways. So the first way, is it primitive material or is it processed material? So primitive material, original solar system material, this is very, very old, 4.5 billion years old or more, and they have a lot of chondrites in them. And the processed material was once part of a planet or an asteroid, some parent body. It's younger than the solar system in terms of age because it's melted or it's metamorphic, it's partially melted. And these are the achondrites, the irons, and the stony irons. So the primitive material condensed directly out of the solar nebula. Mostly in the asteroid belt, but also further out. It depends on temperature. So the asteroid belt is about 2.2 to 3.2 AU from the sun. So between Mars and Jupiter in this general area. So the stony chondrites formed closer than 3 AU, and the carbonaceous formed beyond 3 AU because there it was cold enough for the carbon compounds to actually condense. Anything closer, and they're just, they're still in a vapor state. And these primitive meteorites tell us about the early solar system and what it was composed of. The processed material comes from larger objects in the inner solar system. Metallic meteorites are their fragments, like I said before, cores of larger differentiated asteroids that were blown apart during collisions. What we have here is an iron nickel meteorite, and these etchings, they're Widmanstätten patterns, I think, something like that. And the German guy who found them, he had an iron meteorite, and for kicks and grins, he tried to polish it and then tried to clean it up with some acid. And when he did, these structures came into view, and what these are various different crystals of nickel iron. These crystals take a very, very, very long time to form. So we're looking at timescales of hundreds of thousands to millions of years of slowly cooling. So we cannot replicate these on Earth because we don't have an oven that can cool something slowly over a couple tens of thousands to hundreds of thousands to millions of years. Now, we don't have the time. But in an asteroid that's been slowly cooling over a long period of time, over billions of years, crystals like this have time to form. So these are from the cores of these asteroids. And we also have processed material that comes from planets. So rocky meteorites that were chipped off the surfaces of asteroids, Mars, and the moon, they're all younger than the solar system because they've been processed. And different types reflect their origins. We have the achondrites, like this one. This is a lunar. This is Northwest Africa 11421, and this is one of Marcin and Thomas's finds in Algeria, in Tindouf. I actually have two of these, so I will be showing this one. We have the iron nickels, we have pallasites, and we have the mesositerites. So chondrites, what do they tell us? Chondrites are the earliest, they're the oldest material in the solar system. It's the most similar stuff to the early solar system. So chondrites have these little, you can call them balls, they're called chondrites. And they're just going to be scattered throughout the thing, and there's a matrix that holds it all together. So because they're spherical, we think they're originally molten droplets, and we think it condensed out of the original gaseous material of the solar system. So the abundance and types of elements in the chondrites are very similar to the atmosphere of the sun, and this is why we think that that the chondrites tell us what the early solar system was pretty much made of. So most chondritic asteroids are affected by impacts, and we have shock processes from those impacts that blew off rocks that eventually landed on Earth that we have as meteorites. And there are very, very few chondrites that we have which are pristine, which are unaffected, which were either from very, very small asteroids or they weren't impacted by shocks. And these are very, very, very important. We'll get into that too. So achondrites, typically lunar, Martian, the head group from Vesta, or primitive achondrites, which are this own weird category by themselves. This is actually a, what is this? This, I believe, this is a Howardite from Vesta for this image right here. And achondrites, they're rock samples from various objects in the solar system. They tell us the rocks on other planets, and almost all of them are from Vesta, from a massive collision. We have the Howardites, we have the eucrites, and we have diogenites. And we'll get into those as well. So the other method for categorizing them, we have stony meteorites, we have iron meteorites, and we have stony irons. So the stonies include the chondrites and the achondrites. They're mostly rock. The chondrites have a little bit of iron in them, but not very much. And it should be very, very little or none for achondrites. And about 86% of all meteorites are stonies. They're the most common type by far. We have carbonaceous chondrites. These are the oldest and the rarest chondrites. They have very complex organic molecules with amino acids, fatty acids. And it is possible that, with panspermia, the idea that there are meteorites that contain these building blocks of life that landed on Earth, or that possibly contained life itself and started to replicate, that these were like seeds for planets. We also have stuff called calcium aluminum inclusions, which are really, really cool. They're these little bitty flecks of calcium aluminum, which only forms in a supernova. Well, we find these in some very early chondrites, and they're just embedded in the matrix. And what we think is that this is the remnant of a supernova that exploded close to the Nursery Nebula where our sun was formed. And these calcium aluminum bits blew into the nebula, created the initial shock wave, which started differential density layers within the nebula that eventually collapsed down further and became the sun and became the planets and everything else. And enough of these calcium aluminum inclusions, or sorry, these calcium aluminum bits were included inside chondrites that we eventually found. So this is our one of our biggest pieces of evidence for a supernova as being the initial cause for the formation of our solar system. Stony meteorites. So ordinary chondrites, 80% of all, but we don't think, let me start again. Just because most of the meteorites that we find are chondrites does not necessarily mean that most of the asteroids in our solar system are chondritic. We just don't know that. So there's actually one, Bozenmakova. We think a large chunk of all the chondrites that we have come from that one, this asteroid here, because of a particular impact, because of their composition compared to what we can see of the composition of this asteroid. And here are a couple of others. So like the LL chondrites, like Chelyabinsk, we think it comes from Otokawa. We think we do, and we'll get into why in just a bit as well. So achondrites from Mars. By looking at the rocks themselves, by analyzing the isotope ratios in the rocks themselves, trapped atmosphere, things like that, we can compare it to what we already know is on Mars based on the probes that we've sent there. And we can say, yes, these are Martian rocks. For lunar rocks, we can compare them to what the Apollo astronauts brought back, and we can say, yeah, these match up. And that's how we know certain rocks come from Mars, certain rocks come from the moon. And we're able to do that now, definitely with a very, very high degree of certainty, because we can do that direct comparison. Previously, we were highly suspicious that these rocks did come from Mars, did come from the moon. We just couldn't be absolutely sure. And it actually wasn't until the Dawn satellite visited Vesta in early 2000s that we were able to confirm that Howardites, Diogenites, and Eucrites came from Vesta. And here we go. So we have the Howardites, the Eucrites, and the Diogenites. So I think it was between 25 and 35 million years ago, there was a very, very large impact on Vesta. It gouged out a huge chunk of it and created the asteroid group known as the V-types. And we think those are all from this initial impact. Well, a lot of them landed on Earth. So we have these Howardites, which come from the crust area, the regolith up there. We have Eucrites, which appear to be magma from the mantle, but not mantle material. Think of it kind of like a basalt, not exactly. And we have Diogenites, and we have deep Diogenites and shallow Diogenites. So the deep ones are are olivine-rich Diogenites, and then you have other Diogenites as well. So this on the right would be a Howardite, And this on the left would be a diogenite. There's not an image of a eucrite here, but I actually have one. I have actually all of these. So, okay, nickel iron meteorites. So they come from the cores of larger asteroids that were blown up. The nickel iron crystals, they're visible once you polish it. Actually, I've got this one too. Got it right here. So you polish it up, and then what you do is you etch it with an acid. Typically use like a aqua regina. It's a nitric sulfuric acid mix, but you don't have to leave it on very long. Basically, you just want to wipe it on there. It does not have to be high strength. Give it like a minute or two, and then neutralize it. And then you definitely want to rub it with oil, and you want to keep your meteorites well oiled. They will rust if you don't take care of them. And there are some, the name escapes me. I want to say it's Fukang, but it's not. It's something else. There is a Chinese palisite, which is very, very, very pretty. And they make it into pendants and jewelry, and you can find those on eBay all the time. I highly recommend not buying those. They have a very high chlorine content in them, and if you look at them funny, they will rust. If they're not covered in like an epoxy, they will rust. If you don't keep them in oil, they will rust. So this beautiful piece of jewelry that you have, like buy it for yourself, buy it for your spouse, have a ring made out of it. You may take it off, you may put it in your jewelry case and leave it in there for 3 or 4 months. Come back to it, and now you have a lovely pile of olivine crystals sitting in rust. Just a little bit, and it's gone, because people typically don't know this, and so they're not told about it. Well, now you know. So these, again, these indicate that the original asteroid must have been large enough to be differentiated. So just think about that. An impact large enough to break up an asteroid that has a crust, a mantle, and a core. And then we have the stony irons. So they're a mixture of materials, iron and stone. We have the mesositerites. So the mesositerites, they're iron flecks in a silicate matrix. Could be metamorphic, we don't really know for sure. And we have the pallasites, which are olivine or peridocrystals in the iron matrix. Pallasites come from the boundary layer of the mantle and the core in these large differentiated asteroids. We all think they're the prettiest ones. And you can find these online as well. So this is that Fukang. This is the stuff that people make jewelry out of. Not just these, but typically these are for pendants. They're very, very pretty. They're very, very difficult to slice thin enough where the light from behind, like a backlight would, like this, will show up at what the crystals look like. These form, let's go back. These are very, very rare because of their formation. They're formed where the mantle material and the core material start to intermix. So peridocrystals, they're typically found in the very, very lowest parts of the mantle in large quantities, but you can find, you basically find them suspended in that boundary layer between the core and the mantle. So the rocky material, it's just too hot for the rocky material, but it's not too hot to melt these peridocrystals. And so they're kind of migrating down, and anything that goes further down gets melted into the matrix. Anything further up is just mixed in with the silicate of the mantle. But this boundary layer is where you find these. So you find a lot more iron because the rest of the core is rather big compared to this boundary layer. So why are meteorites important? They tell us about other worlds, our solar system, and how the solar system and our planets formed. They're a free return sample mission from other planets, but it is a random sample. You get what you get, and you love what you get. That's it. So you don't get to choose what you get. You just pick something up and you hope for the best. And for the contracts especially, they're time capsules from the early solar system. How do we know where meteorites come from? So if we have a meteorite on hand, so we have a meteorite on hand, what can we do? Well, we can cut it open, We can do analysis of it. That way we actually have it in hand. We can analyze it. But how do we know where it came from? We look at other similar sources in our solar system. And the way we do it is we bounce sunlight off of asteroids, look at the wavelengths of light that are absorbed and reflected, and make a comparison with the stuff that we have. Good night. I have my son here is going to bed right now, so I have to wave through my window. So we can look at the reflection of the sunlight coming off of these asteroids, and we can analyze the material at that location where we're looking. So if we have a satellite there, we can do a much more detailed analysis of the surface. We can have fairly decent resolution of a very small area. But if we're doing something from the Earth, we really can't do that. It's kind of the whole picture. We can see everything that's on the surface, but only what's on the surface. So in this case, we have Renazo, which is a known a carbonaceous meteorite, and then we can compare it with Pallas. So just by analyzing the light coming off of Pallas, we can match up the curve pretty well. So this is why we think this meteorite comes from this asteroid. Again, we're not 100% sure, but we're fairly confident that this is the case. For meteorite hunting, so the American Meteor Society, they have a website, and it tracks fireballs and bolides around the world. People will go on there and they will go ahead and say, I saw this object at this time. It started this part of the sky. It went to this part of the sky. And it was this bright, et cetera, et cetera. From that, they can triangulate a pretty good position of where they think it entered the atmosphere, when it was no longer visible. And then from there, people could say, okay, now where could it have landed? So they get stuff from photos, they get stuff from videos. Some people have doorbell cams right now that they can submit that video as well. And from there, it's relatively easy to analyze. You can say, well, we know what this camera is like. We know what the lens is like. We know what these angles are like. We know where the house is pointed. So they can figure the rest out. It's just math. So for this particular one that came in, we can see where it started high in the atmosphere and where it came down right here. So this is where it stopped being bright. This is not where it came down. At this point, it is still, let's say 20 to 30 kilometers up, maybe more, maybe a little bit less. So the question is, where did it actually land? It can keep going, but not very much. And here's why. Just because it enters the atmosphere at 11 to 72 kilometers a second does not mean it's going anywhere near that fast once it goes to the end here. At this point, it may be going only 400 miles an hour. And by the time it hits the ground, it may only be doing 200 to 300, maybe 400 miles an hour. So it impacts not very fast at all in comparison to how fast it was going when it hit the atmosphere. On top of that, now it's falling through, let's say 20, 30 kilometers of atmosphere. The winds are now buffeting it. So it doesn't come down straight. It doesn't even come down in a ballistic path necessarily. If the upper level winds are pushing it against the direction of which it's going, now it's going to slow down even more. It's going to drop faster. Winds at lower altitudes can now push it in different directions. So you think it's coming down, well, it's going to land over here in Rush Hill. That's not the case. If there's a strong southerly wind, it may be over here in Ladonia, or it can be even back here towards Middletown. Probably not the very far here, but it may be somewhere in this area. We just don't know unless you take into account the winds at that time. And we do not have a really good picture of wind conditions, wind directions, wind speeds at all levels of the atmosphere at that moment. The only way to do that is to launch weather balloons, and you'd have to be launching weather balloons constantly to have that kind of data. So it's a guess. It is entirely a guess. You look at the weather and you say, well, maybe somewhere over here. So it's a quick story. Back in, I want to say the early 2000s, we had a fireball over Fort Worth. And it was a little bit it was basically just over Fort Worth. So two of our club members actually went out to go find it. They went down to where they thought it may have landed, and they started talking with people in that area. And they went to gas stations and said, "Hey, was anyone working here last night? Did anyone see the meteor?" And people said, "Yeah, I did see it. It was over here, and it came down like that." I thought, okay, cool. So they could plot some of that out. Now they went other places. They actually went, I think, like in a 50 or 60-mile radius, trying to find people who saw it. And finally, they got to one side, says, "Yeah, I saw it in this direction, and it came down like this. Or it was almost overhead. It came down like this." They took all that information and they put it into a map, and they got a general area of where they think it fell. So they went out looking, and it was cornfields. So you're not going to find anything in cornfields, but they decided to just go ahead and start walking on this country road. And it was a paved road. Down here in Texas, I don't know what you have, but we've got asphalt roads and covered with gravel, and they're pushed down with the roller. So they're walking along this country road, looking down, and they managed to find 3 small fragments just in the road. They weren't very big. They were pea-sized, but they managed to find 3 fresh-looking meteorites, and they were able to test them. And they're not 100% positive, but they think those are fragments of the fireball that came down. And they were able to find them within, I think 3 or 4 days. So they took their time looking and doing interviews, but it was a fresh meteorite. So more meteorite hunting. You can find meteorites best in places where they stand out. Again, are they going to stand out in a forest? Probably not. And then they stand out in a cornfield? Probably not. Are they going to stand out in the Sahara? Yeah, because the Sahara rocks are bright, they're sandy looking, they're a completely different composition and color than the meteorites. So rocks that don't belong are going to stand out. In Antarctica, if you're out in the middle of the ice floes or the glaciers, if there's a rock sitting out there, you're probably going to notice it. And this is actually something that people in Antarctica do. When they're flying by helicopter, usually there's one person whose job it is just to look down. And their job is, do you see anything weird out there? Do you see any black rocks? If they do, well, they'll usually just land very quickly. If it's a rock out in the middle of where it should not be, they can go ahead and take pictures, get the exact location, pick it up, drop it in a baggie, and keep on going. And now they found a meteorite. It may be important, maybe just an ordinary stony. You don't know until you analyze it. So Antarctica, Greenland, deserts. The Sahara is a good place. The empty quarter in Saudi Arabia is a good place. In Oman, pretty much any place you have this bright sand. In the Sahara, it's not really sand that you have in a lot of these places. It's kind of I forget the term for it. I just forgot what the term for it is. But you can see from here, it's these little rocks on the top surface that it's hard enough that you can drive on. The wind pushes the sand away. So the sand blows off into dunes, and what you're left in is this thin crust of these like little bitty rocks, pebbles, gravel almost. And you can step on it, you can drive on it without any issues, without much issue. And these are really good places to find it. If a meteorite lands on a sand dune, you're probably not going to find it unless you get there very quickly, because the wind will go ahead and cover it up. In Antarctica, again, it's ice. You can easily see it. Not just that. Here's another one. So you don't typically find them in grasslands or forests or lakes or your backyard. If it falls in the ocean, you're not going to find it. If it falls in your backyard, you probably won't notice it. You just think it's just another rock, especially like if you have a rock garden. You may have a mixture of all sorts of different rocks, and there's just this one rock is darker than the rest. It's just not that noticeable. But if you see something like this sitting out in an ice field, well, you're probably going to notice it. So it just doesn't belong. In this case, we also have in the dry valleys areas of Antarctica, you have the ice which actually moves the rocks to places where they're easily visible. The ice comes in very, very slowly, pushes it off. And so all these red flags here that you can see, these are all places that are marked off as a potential meteorite. They're rocks that don't look like they belong in the area. And all of it's been moved. So this landed further out in the ice. It just slowly was migrated by the ice to these locations and then just dumped. So the very first step is you go through, you mark off everything you think is a meteorite with a flag, and then you just keep going. Then the second pass, you come over and you look at each one. You take pictures of it, you mark its location in GPS, you tag it, you bag it, and then you go on to the next one. Bag it, tag it, whatever the order is. Did I find a meteorite? Nah, you didn't. I mean, it is highly unlikely that you found a meteorite. It's probably just an earth rock. I've had lots of people say, oh, I've got this meteorite. Grandpa had this meteorite. Chances are, no, it was just an ordinary rock. Unless they were a collector, unless they knew what they were looking for, it was probably rock. Yes, we hear the stories about the meteorite that was a doorstop for years and years and years because great-grandpa found it. Or the rock that's up on the shelf that that great-grandpa said he saw come down on the family farm. Those are incredibly rare one-off occurrences. The vast majority of the time when someone says, I've got a meteorite that I found, it turns out it's not a meteorite. So you look for a fusion crust, smooth surface. Does it attract a magnet? Not every meteorite does attract a magnet, but most do. If it attracts a magnet, it is more likely to be a meteorite, but not necessarily. I'll show you. Is it heavier than most rocks its size? That's actually a really important one for density. So most meteorites are going to be a lot more dense than earth rocks because they contain nickel iron. That increases density. And so if you have an earth rock and a meteorite of roughly the same size, the meteorite just feels heavier. And it's hard to quantify exactly what I mean by that. You just know it. If you've been handling rocks for a long time and just picking up normal rocks, when you pick up a meteorite, it just feels different. It feels a lot heavier, and you'll know. That's the best way to describe it. You'll know something's not quite right. Meteoroids. I love this. Meteorites and meteoroids. So most rocks that people think are meteorites are really just earth rocks or industrial slag and waste. These are weird looking rocks. They're not meteorites. Some are dark. They're not meteorites. This is slag. This is slag. This is probably This is a volcanic rock. This is a hematite conglomeration, I believe it's called. This is more industrial slag. So, yep, that's the end of that presentation, but I have more. So if y'all are interested, I actually have a sample of meteorites that I can show. Or first we can say, does anyone have any questions? Any questions at all? You can also put them in the chat. And Alex, you can read off the questions as they come in. The chat might be a better way to write down like a complete thought. Sometimes it's hard to get it out on camera. I know sometimes it is for me. I'll go on. How are we for time? Are we good on time?
Reasonably good. I mean, we're close to an hour, but you know, do what you need.
I can talk for 3 hours if you let me.
Well, let's not go that far.
All right, so here we go. So this is actually the first meteorite I ever got. And it's really pretty. I think it's really pretty. This was cut just slightly just to see what the interior looked like. But it's a fairly old one, so this is kind of oxidized a bit. And it's got this smooth kind of melty appearance. And it's just really pretty. I don't think I'll ever cut this one. But this is what meteorites typically look like. Here's another one, very similar color. And this one was cut as well. And this one is totally raw. So this is a fragment, and you can see one side is smooth and shiny. Let's get this way. One side is very smooth and shiny. And the other side, hopefully the focus is going to be pretty decent on here. Hard to tell sometimes. On the other side is very rough, and it might focus better on that. So the rough side is where it broke up in the atmosphere. So I have, and these are Northwest Africa's, but they're unclassified. So they're not important enough to get a name. If a meteorite lands in a location and it's important enough, it gets a name. And typically for Northwest Africa, because there's so many found out there. And honestly, it's the Sahara. What's in the Sahara? Nothing. It's vast stretches of nothing. Oh, there's this hill formation here. What's it called? Nobody knows. Nobody cares. No one lives anywhere near there. No one's bothered to name it. It's just that hill or this valley. If no one lives there, if no one lives within 100 miles of there, nobody cares. It doesn't have a name. So all these meteorites, if they're important enough, they just get a number. And there are so many of them that, you can't name it Sahara, something. We just call it Northwest Africa. If it's Morocco, Algeria, all that whole area, we just call it Northwest Africa. So these are all Northwest Africas. And again, you can see kind of a broken part here and more smooth and shiny on this side. So these were relatively fresh. This one is not. This is not a fresh meteorite. This meteorite, in fact, I actually have two pieces of it. I'm missing the middle slice because I didn't get it. This one was actually in the ground like this. The top surface was, you can see it's got this kind of crazing, kind of cracking feature on it. This was sandblasted 50 years, 100 years, no idea. But this was sticking up out of the ground. This part was the part that was embedded in the ground. And what we have here, when I flip it over, is the inside. And the inside looks completely different. I wish the focus was better on here. Will it focus? There we go. So you can see these cracks in that darker material. Well, this is kind of interesting. This did not crack during entry into the atmosphere. These cracks in that darker material is actually metamorphic. So these are remnants of an impact on an asteroid where it actually crushed the rock, cracked it along these lines, and then remelted. On the other side, you can see how the cracks go all the way through. This ridge here, along these cracks, it's much stronger material than the matrix in between them. So this is metamorphic material. This is a processed chondrite. And you can see there are little bitty chondrules all through here. Kind of hard to see, but also if you can see these little shiny bits in there, those shiny bits are actually iron. I can see one right over here. There's that shiny bit right there. That is a little bit of iron. And this is a couple magnets, and it sticks. It's sticking to different places on here in different amounts, but it's, yeah. So you can see the magnets sticking to it. So again, this is a way to test for meteorites. You just get a little magnet and it will stick to these rocks. For some of these, it sticks just a tiny, tiny amount. You can feel it. What typically people will do is they'll tie a small piece of string, like they'll make a little necklace. They'll tie a piece of string to this, and they'll bring it close to it. And if it just moves, they'll be able to tell it's fairly sensitive that way. This one, Yep, it sticks a little bit more. So it just depends on the rock. Some of them have more iron, some of them have less iron. And I also, when I do outreach, I also bring my meteorongs. This is a nice piece of gneiss, and this is a piece of limestone. Both of these came out of my garden. And the reason why I bring this out is because I can say to little kids which ones are meteorites and which ones are earth rocks. And I'll put out a couple of magnets for them to play with. And do the magnets stick to those? No. Do they stick to this? Yes. So this is a really good way to educate not just kids, but adults what meteorites look like and compare them to several. I usually have like 4 or 5 different earth rocks and say, well, this is smooth. This is kind of shiny too, right? Well, this is smooth and shiny. Are they the same? No. And then they can also feel the weight differences between them.
Hey, Chris.
Yes.
We got a question in the chat, and it's a good time for it since it's a meteorong. Can you define what slag is, where it comes from,
Oh, yeah.
why it's found out in the open, and why it's confused with meteorites?
Oh, yeah. So hang on. I have one of those right here. I need to step away for just a moment. What do I have? I have 1.8 kilos of what was purported to be a iron meteorite on eBay. This is it. So this is a piece, I'll do it on the big camera so you can see. This is how big it is in scale. It's heavy. This is actually 1.8 kilos. And so this is a chunk of Chinese steel. This is waste. So this probably fell off of a smelter and landed on concrete. And there's actually a fold right here where it kind of landed, plopped over, and then just did that. And eventually it just hardened up, and then it was tossed away into a river. So this was sold on eBay as a meteorite, and it's shiny, and it's dark, and it's very, very heavy for its size. And if I take a magnet to it, oh boy, yeah, that just sticks right there. I can just do that there. The magnet sticks really, really well. So this is a remnant of industrial processes that they then just took and dumped into a river. Somebody found a bunch of these in the river and thought, well, it must have been a meteorite that landed in there, or they knew it was slag and they just stole it on eBay anyway. So I bought this thing for $80, shipped from China, because the pictures weren't terribly great. And I thought, I'll risk it. And I got it. And within about a half a second of me opening the box, I knew this is not a meteorite, even though it was so heavy. And then I also did a quick nickel test. And this has very, very, very little nickel. You can actually buy these nickel tests. And what you do is you'll grind off a little bit, and you'll put down a drop of the material, a drop of the liquid on there. And if it turns green, then it means that there's nickel content in there. And typically for most earth steels, it's like a percentage or less. Meteorites, it can be anywhere from 5 to 20% nickel. So there's a lot of nickel in there, and the nickel test really lets you find it. So I did not waste $80, because I emailed the guy back and I said, this is not a meteorite. I want my money back. And he goes, okay. So within, I think, like a week, I had my money back, and he didn't ask for me to ship this back. And honestly, I wasn't going to ship back 1.8 kilos of waste steel back to China. So this I bring out as my big meteorong, don't buy meteorites from China off of eBay example. And I went through the process so no one else has to, hopefully, if they listen. So what slag is going to be the material that when you smelt iron, you blow oxygen into it to burn off impurities. It's called the oxygen lance. And what you're trying to do is you mix it up, and anything that's not iron will get oxidized and will float up to the very top of the smelter, the crucible. So all that stuff on top, you rake it away and you let it drop off and let it cool down, and then you just come in with your front loader and you get rid of it, and that is slag. So slag is going to be a mixture of iron and various other impurities, usually rocks, usually like it's just silicate material mixed in with some iron material, and it's a waste material of making iron, and it looks weird. It always looks weird. Sometimes it's bubbly, sometimes it's kind of ropey. It just depends on the silicate mixture in there. But just think of it like molten rock mixed in with some iron. So just because it looks weird doesn't make it a meteorite. And yeah, but you find all sorts of stuff like that that's being sold on the internet that says, yes, this is a genuine meteorite. Well, it's not. This is, let's see that Northwest Africa 10331. There are 4 pieces of this one rock in the world. I have one. My collector friend in Canada has one. Thomas has a 3rd piece, and the last piece is owned by another collector up in Canada, a friend of my dealer. Well, the interesting thing about that is this is a primordial meteorite. So this, I'll bring it a bit closer. You can see all those little flecks of iron all in there. But this is a remnant of the early solar system. This contains material from the early solar system, and this also contains calcium, aluminum inclusions. And the reason why this one is important is because this rock tells us a lot about the early solar system, to the point that Tomasz told me that he lent his piece, his end piece, to a Polish grad student who was working on on his or her, I don't remember who, on their doctorate thesis on early solar system origins. So my policy has always been with mine that if someone wants to borrow one of my rocks and use it for scientific research, I would be most happy to let them. I don't mind if they take off a little bit off the side and write a paper on it. Just add my name to the paper as thanks, and that'll make me happy. But this one is 163.6 grams. So you can see it's fairly thin. It's a nice thin section, but it's very, very pretty. It's very, very interesting. And this is a mix of iron with those calcium aluminum inclusions. So the iron typically is these like, it's like roundish. They're going to be the rounder kind of blobs in there. And the stuff that's like these long bits, these are the calcium aluminum inclusions. But yeah, there's so much iron in this thing anyway that the magnet is going to stick out. So there was a chat about somebody having a rock that they wanted to show off. Well, if you can bring it on camera, you can take a look. But again, the easiest way to do it, magnets. It's far more likely it's a meteorite if there are magnets.
Yeah, I'm trying to bring my video back. Oh, there's start video. Okay. Oh, so the host is going to have to restart my video.
Yep.
Let's get that real quick. Let's see, find you.
These are some irons, and I don't know how well we're going to see these. You got it?
Yes.
Okay.
Basically, I don't know how well you can see it, but you'll notice that there is a magnet, a rare earth magnet sticking to the bottom of it, and it's quite dense. It's basically reddish color, but it's not really all that smooth. I've been wondering about this thing for years.
So is it rusty? Is the outside very rusty?
It's definitely a slightly rusty reddish.
That's probably going to be a hematite.
Okay.
it's probably going to be a hematite. And the reason why I say that is because with stuff like these are going to be, they have iron in them, but there's no rust on the outside.
Right, I see that.
Yeah, with the irons. So for example, here's an iron. This one is in the baggie because it's covered in oil.
Right.
And it's got a little bit of rust on it, but not very much. If you could cut it open, what you'll see is clean iron like this. Okay. If it's rusty all the way through, that's going to be a hematite.
Right.
So that's the risk, is you're going to cut it open and see what it is. Now, I don't necessarily like to cut meteorites open, but when I talked with I talked with Marcin and with Tomasz about this, and what Marcin said is, I've never cut a meteorite that didn't get more expensive. So just by cutting it, just by seeing what was on the inside, he was able to sell both halves for more than how much he would get for the original one.
Yeah, frankly, I'm guessing it probably is a hematite because based on what you're saying, because the surface really isn't all that smooth. It's not like it doesn't really have. I felt enough fusion crusts. This doesn't feel like that.
Yeah, then it's probably going to be a hematite.
Yeah,
my focus was a little bit better on this thing. It's hard to do with that one. So something about the fusion crust. You know what? Let's do this. So I'm going to switch over to a microscope.
It's a nice piece of hematite, but it's terrestrial. I always kind of figured that was my default. It's not a meteorite unless somebody who knows more about them tells me it is.
So that's probably going to be a hematite. I'm
right.
Terribly sorry.
Don't be disappointed. It's one of my favorite rocks anyway.
That's absolutely fine. It's whatever you love. If you like it, fantastic. That's what's important.
It's my paperweight.
Oh, that works too.
On my desk.
I haven't even thought about using my slag as a paperweight at all. It just goes in the kit. So this is a eucrite. This is a pyroxene and plagioclase on the inside. Do I have a pen somewhere? Oh, there we go. I got a pen. I really need a needle. You know what? I've got something. Yeah, let's see. Oh, yeah, this will work. So what I want y'all to see is this. This is a cheap little $20 microscope from Amazon. It is worth it. So the black stuff over here, this is the fusion crust. This, the white stuff and the brown little brown sugar and white sugar looking crystals, these are the plagioclase and pyroxenes. But if you look right there at the edge, that fusion crust does not extend at all into the inside. It looks like it's almost painted on.
Yeah.
And this is what you see with fusion crusts all the time. So I love this one. This one's just such a pretty, pretty little rock. It is a small fragment. This is Tierhert from, I want to say Morocco. And I talked to the guy who found this as well. And it's this one I actually got from my dealer in Canada. He actually sent this one to me for free because I said the magic word. I said outreach. And he actually sent me a couple of other things for free because he knows that I do outreach events with these, that these aren't just going to sit in a collection somewhere and gather dust for only my enjoyment. This is something that I like to share. So this is an exterior fragment, but it's got the fusion crust on there. It's very, very pretty. And then I've got this one. This is Northwest Africa, 8327. And this one's really pretty. You know what? I'll do it.
Yeah.
I've heard it on here first. Let me switch to that view. So you can see just how big this is. It's not very big. This is Northwest Africa, 8327. It's chondrite LL5, and it's only 7 grams. But it's, to get that focus better. You know what? I got to get this out of the way so it focuses just on that. Come on, camera. Maybe not. It's got a hard time focusing. See how close I can get it. I hate this camera. It's my webcam. I thought it was going to be a little bit better, but it's not. So let's get under the microscope. And under the microscope, it'll be a little bit better. So I'd have to change my focus on here. Zoom out a bit. There we go. So these are little bitty chondrules. All these little round bits, these are the chondrules. And then the shiny bits, like that, this is little flecks of nickel iron all through here, shiny bits. And the chondrules, like this one here at the edge, they're round. Here's another one. All these round bits, all these dark round bits, these are the chondrules. So this is a slice of the inside. And if we go to the edge, you can see the black. I'll try to put something right behind it, underneath it. There we go. Now you can see the fusion crust and just how thin it is. It's just barely there. It doesn't even penetrate the width of a single chondrule. It's almost like it's painted on, but it's not. And one of my coworkers, he's a bit of a smartass, said, when I was showing him these, he said, I've got a bunch of meteorites in my backyard. I'm just going to take a blowtorch to them and get them all black on the outside, and then I will sell them to you. And I had to tell him, well, that's not the way it works. So we actually can't have, we have not been able to create heat that high lasting for such a short period of time that it would just ablate the outside of the meteorite without going to the inside. So what's happening is it is actually ablation. The outside of the meteorite is burning away and going away and taking away the heat so it doesn't go to the inside of the meteorite. Because if I flip it over, that's the fusion crust on the outside. And it gives no indication of what the inside looks like. And just looking at it, it's a very, very pretty rock. And people will typically say, you know, I'd love to get like a countertop made out of this. It looks almost like an Italian terrazzo. And, you know, yeah, a countertop would be great. But this goes for probably about, you know, retail, maybe $2 to $5 a gram. So that's going to be one expensive countertop. It's going to be a really expensive countertop. Yeah, so that one is Northwest Africa 8322. And then the favorite one, my little lunar, or one of my lunars. So this is a sample of, this is basically regolith. Sorry, not regolith. This is, should I remember, this is lunar highland silicates. It is a, it's from Tindouf, Algeria. And the entire weight of the whole thing was 912 grams. And this is just a 2-gram sample. So you can see the darker material. The whiter stuff is more plagioclase and pyroxenes, mostly plagioclase. And the dark material is a matrix. That red bit, I'm not sure what that red bit is. I think it's just a stain. It could be just an iron stain on there. There may have been like some little bit on there that rusted. The other side, it's more of the matrix material and holds these larger gray kind of, you know, I don't even know what to call them. They're not chondrules. They're just like little bitty bits of gravel, little fragments. I have another one, and I have no idea how well this is going to work out. I actually have it in this little case. So I have to figure out how to open this case. Oh, there we go. Because it's kind of neat. It's this plastic, like a shrink wrap plastic almost. And I can't open it. I have not tried to open this in a while. Oh, there we go. Okay. So this one is an end piece, and it is the same rock, but it's polished. So put this into place. So on the polished side, you can see these this round clast, I believe it's called. And then you have the smaller ones, and you have that gray material. So this matches the stuff that Apollo brought back in terms of composition. This is why we know this is a moon rock. And the other side You see a bit of that same clast right there. I'm not even sure what that red stuff is. I want to say it's just rusty iron, but I'm not 100% positive. But it is a very pretty rock, but this one is very, very delicate. And so it stays in the case. I don't typically take it out. It's just for show, but this smaller one that's not polished nicely, this has a good shape. It's fairly strong. And this is a nice one that I like to give to kids so that they can play with it. So I'm gonna try this. Don't have to zoom in so much. Let's get a good focus though. There we go. Yeah, so you can see a little bit better. That's kind of nice. Kind of nice. I've been playing around with taking photos of all these at super high resolutions, because this is not, just to catalog everything. And so I've got like my macro set up with macro stepper rings, and there's a way to do it. And you take, because the field of view, sorry, the
Depth of field.
Yeah, depth of field, thank you, on macro photography is incredibly small. So the trick is you take like a dozen photos and you just change your focus just slightly, in which this case I have to be moving the camera just slightly to get all those different layers. And then there's, the way I used to do it would take me a couple hours to do. It turns out with the newer versions of Photoshop, it can do it automatically.
Photo stepping, yeah.
Yeah.
I mean, focus stepping.
Yep. And it what took me hours to do now takes like 4 minutes or less. So it's a huge, huge time saver. I also have this one. This is actually, if I think this is the right one. I'm not 100% positive, but I think this is the right one. I think this is the Sugartite. I think this is my Martian. Yep. This is my one and only Martian. So now what's kind of interesting is that lunars used to be really expensive. They used to be about $1,000 a gram. And because of some of the ones that were found recently, the price has dropped down. It's kind of fluctuating right now. It's been as low as about $100 a gram up to around $300-400 a gram, but the prices have dropped down quite a bit. Same thing with the Mars rocks. They used to be $3,000 to $5,000 a gram, and they've dropped down now to probably about $600 to $1,000 a gram. It depends on which ones. And this one was one of the ones that was found. This one is from
Shurgahi, Russia.
No. This one was found. This is in Northwest Africa.
Oh, and then
this is from my dealer who lives in the Shetland Islands. And Fabian. So Fabian lives up there with his wife because she's a geologist and she loves rocks, and the Shetlands are fantastic for geologists. So he lives like on the northernmost island, inhabited island on the Shetlands. And I talked to him one time. I said, "Why do you live up there?" and that's what he said. So, but they make a trip down every couple of years, or they did before they had their kid, just like us. They made trips down to Northwest Africa, and they would do their meteorite hunting. And then he would cut up the meteorites into these small little samples, which is what I love. I love these little small samples because I can get a bunch of them without breaking the bank. And now I have samples of different locations that I can say, well, this is from here, this is from there. And it's just really, really neat, the kind of stuff that you can do. And where is my...
Chris?
Yes.
Let's start to wrap it up. I mean,
Okay.
getting on towards 9:30 up here, and then we can shift off and maybe talk further in our social section. But
then I've got one more to show off, and this one, it's just got a fun name. Vaca Muerte.
dead cow.
Dead cow. And dead cow comes from Chile. So this is, I think it's in the Atacama somewhere, but I'm not 100% positive. But this is a mesosiderite. So this is the opposite of a palisite. So the mesosiderite is these little flecks of iron, in a silicate matrix. So, the meteorites are named after the places where they land. So if you have and it's not the place that they land necessarily, it's the geological feature where they land. So if you're looking at the meteor that created the Barringer crater or meteor crater in Arizona, it's not called Barringer meteorite. It's not called meteor crater meteorite. It is called Canyon Diablo. And it's called Canyon Diablo because that is like a geological feature that is nearby. And so Vaca Muerte is actually the name of a geological feature near where this was found. But I just like this one for the name. And it's also heavier than you expect a little bitty tiny rock to be. So it's not very big, but it's interesting. And I have another mesosiderite. I think it's a mesosiderite, but it's a unclassified Northwest Africa. And the way, if you have a meteorite and you think it's important, if you think that, yeah, this is something that I want to get analyzed, you can actually send it to various places. There is I know that Thomas and Marcin work with, I think like 2 different universities in Germany, and they get them analyzed there. So they do the cutting, they send them there, it gets analyzed, they come back with, oh, this is this type of meteorite. And then, in the case of like lunars or the Martian ones, well, those now fetch a really nice premium and they can make a lot of money. So as a quick one last aside, and then I'll be done. So the way they do the meteorite hunting is they will go down and usually spend 3 or 4 weeks living out of the truck and driving along in the Sahara. So one person looks to the left, one person looks to the right, and one person drives and looks forward. And if they see anything, they'll just say, stop the truck, and they'll stop, they'll pull over, they'll go out, they'll make sure it's a meteorite, catalog it, bag it, tag it, bring it back. So when they do their trips, it's not really that they come back with, 1 or 2 or even 5 meteorites that they find out there. Marcin said that on their, was a trip that they took in 2018, 2017, they came back with about 150 kilos of rocks. So that does not really fit in your carry-on baggage. So they crate everything up and they ship it back to Poland. And then they spend the next couple months going through all of it and cutting, because these things take a long time to cut. Remember, they're very dense. They have a lot of iron in them. So you're going to lose up, and you want your saw to have a very, very tiny kerf so that you lose as little material as possible. So it just takes a very, very long time to cut. And Marcin actually built this specialized slicing machine. It will go all night long just to cut a rock, that thick, and constantly drenched with water. So I would love to go on a trip with them. I'd absolutely love to go out and ship back, even 20 kilos of rocks. But I've got a 5-year-old, and that's not going to happen anytime soon. And with the situation we're now in, it's not like the before times. So that is not even anywhere near the extent of my collection. I actually have like these display cases next to me over here with more of these little samples. But this is kind of what I go for, is these little samples in little jewel cases, because I can have everything labeled, and it's something that I can take out to people, and I can say, I can put in their hand, and they can look at it and they can see what a meteorite looks like on the outside, what it looks like on the inside. Oh, I didn't even do this one. I've got 2 Chelyabinsk ones. So this one was actually, this is a fridge magnet. So there was a Russian guy who found a bunch of these, just little pieces of gravel. The actual meteorite is just right there at the tip, that little black thing. And all he did was he carved out these little wooden meteors and glued on the piece of Chelyabinsk, and then he was selling them. So my dealer actually sent me this, and he said, yeah, it's just a fridge magnet, but it's really cool. It's just a little flaming piece of Chelyabinsk. So that's all I have. Well, I have more, but that's enough for tonight then. Thank you very much. I really appreciate you giving me time to talk about this. This is
Thank
just a fun topic. So
Very
Thank you very
fascinating.
much.
Very
I'll
fascinating.
stick around if anyone has questions or wants to talk.
That was awesome, Chris. Thank you so much. I learned
Wow.
a lot.
you.
Yeah.
Sign of a successful presentation.
Terrific.
Any last minute questions at all for Chris before we move on to social
What-
hour?
Just a quick, you have been hunting for meteorites, or do you primarily purchase them?
I purchase. Like I said, I've
Okay.
got a 5-year-old,
Yep.
and I have our club members who did the meteorite hunting. They were retired at the time, so they had time to do it. And
Right.
like in Texas, there's no point to hunting meteorites. You really have to go to Morocco. If you want to find meteorites, you just go to Morocco. I do have the one that fell in Costa Rica a couple years back. I have a small sample of that one, Aqua Zeteca, I think it is. But again, it's stuff that I purchase. It's not
Right.
not stuff that I go out myself and do.
Yeah, well, I can understand that.
You
Those
said
go
for
to
the iron
Antarctica.
ones. Oops, sorry.
Probably find a lot in Antarctica. In Antarctica.
Yes.
I think that's not white. Meteor.
Remember the Martian one that fell or that was found back in the was it late 90s, early 2000s, the ones that they thought had the microfossils in there, that was from the Allegheny Hills, something like that.
Alice Hills, I think.
Alice Hills, that's it. So that one was found down in Antarctica in the dry valleys, and yeah, that's. So if you want to spend the time and buy the ticket to go down to Antarctica and look for meteorites, you can probably find some down there if they haven't been snatched up by the researchers already.
What kind of oil do you use to protect the iron-based ones?
Gun oil.
Okay.
I don't have guns, but despite this being Texas, I don't actually have a gun. But gun oil works really well. Even non-vegetable oils work. You want something that's a petroleum. It doesn't need to be thick like Vaseline. Gun oil just works really well. It's got that right viscosity for it, and it does protect it. And also keeping it in plastic baggies, that really helps.
I think gun oil also is a little bit acidic, which helps to keep the surface reduced.
Comment of sorts. I did see one time space junk burn up, and that was spectacular. One of the most, because it lasts a long time, so it gets your attention, and then it's not gone right away, and you can see it for like you said, 10 seconds or more, but you get it breaks up and you get colors. It's really spectacular. Get lucky enough to see it. I thought that was really fun.
Have you, by any chance, been to New York to the